Alright, welcome to your first installment of remote physics or distance learning physics or supplemental learning physics. Anyway, I'm going to attempt to use this kind of this video and this kind of technology to try to teach you from a distance, and we'll see how this works. It's not ideal, but it's right now it's the most logical setup for what I have here at home. So you'll notice that I posted a document that has this here, this little table here, and we're talking about distance, speed, and acceleration, and we're talking about how they relate or how we can define them based on the change in distance, instantaneous distance, average distance, and constant distance, and the same with speed and acceleration. So we'll just do a little bit of, this is what would normally be notes on the board, but we'll just go through this a little bit right now. And then I think I'll give maybe the first 3 questions. I'll go through with that to get you started. And then sometime this week, maybe closer to Wednesday or Thursday, I'll post the remaining questions after you've had a chance to try them out yourself. I also am planning on posting a video about the graphing from last year, or last, I guess, a couple weeks ago. Again, it would have been much easier to do that in person, but just the way life is. So let's get started here. So the first thing I'd like to say about distance is that it's a measurement with the units of, I usually put for units, I usually use a square bracket like this. And so distance is in meters, and speed would be meters per second, and acceleration would be meters per second squared, like that. And when we talk about the change in distance in this first square here, we're talking about simply, we define it as the final distance minus the initial distance. So I'm going to write it up here. I'm going to go delta. We use the Greek letter delta, and I'm using the subscripts F and I for final and initial. But delta, it just means the change in something. So delta D is equal, maybe I'll use arrows just so it's not, you don't think it's an equation. Delta D is the change in distance I'm really hoping it's focusing on the page and not my hand, but again, I'll figure this out a little bit better throughout the week. And the D subscript F is final distance. And DI is initial distance. Now, if you are able to print out the notes that I put on the Google Classroom, then I think it's going to be the most helpful for you to follow along with this and to fill in the notes yourself and to get just used to doing this on pen and paper or pencil and paper. And anyway, so I recommend, if you're able to print it out, awesome. If you can't print it out, you could also, it's a Word document, so you could probably modify it and put in this information in. Okay. You'll notice that the change in speed and the change in acceleration, we're going to define those things the same way. So the change in speed, for speed, the symbol we use is V. It's also the symbol we use for velocity. And the difference between speed and velocity is a vector. So I wonder if I should put that over here. So speed, we give it the symbol of V, and velocity also has a symbol of V, but we often use a little vector arrow above it. And actually it's the same thing up here. Distance, we use the symbol D, And for displacement, we use the symbol d with an arrow above it to show that it's a vector quantity. And a vector quantity, we'll discuss that more, but a vector as opposed to, this is a vector, as opposed to a scalar. A vector tells you the magnitude and direction, and this just tells you the magnitude. So if I say I parked the car 10 meters away, I'm just saying a distance. That's a scalar quantity. If I say I parked the car 10 meters north from where we're standing, then we now have a direction as well. So it's got displacement. And the same speed would just be, I drove to Regina. Oh wait, if I say Regina, now I'm talking about direction. So if I'm from Moose Jaw and I'm driving to Regina at 100 kilometers per hour, 110 kilometers per hour, that's velocity because I've given you speed and direction. But if I just said, oh, I was driving the other day at 65 kilometers an hour, then I've just told you speed. I didn't tell you any direction. And then the last thing is acceleration. And as far as I know, there is no different word for vector versus scalar for acceleration. And you could distinguish them like this. But usually when we talk about acceleration, we usually know the direction, so we're typically, it's implied we're talking about vectors, but I guess doesn't have to be the case. So okay, let's go back to this chart here. So the change in speed is equal to the final speed minus the initial speed, and you could write those things in again. And the change in acceleration, or delta A, is equal to the final acceleration, so A subscript F, minus the initial acceleration. All right. So that's the change, and it's basically the change in distance, speed, or acceleration is just so that when we're clear when we talk about that, we're just defining it as you started somewhere and you went somewhere else. For instance, let's talk about distance. You started somewhere and went somewhere else. What is the distance or the change in distance? Well, you take the final minus the initial. And the reason you don't do the initial minus the final is because, let's say you start at 0 meters away and went to 10, then if you did it the other way, you get a negative number. It would still be correct in a magnitude, but the negative implies, especially for vectors, it implies a direction. Let's go on to instantaneous. Instantaneous, we just give the symbol of D or V or A, and by instantaneous we just mean the distance. The distance of an object at a particular moment in time. And it would be the same with all these ones here. This would be the speed of an object at a particular moment in time, and this would be the acceleration of an object at a particular time. Okay, so that's if you could know the distance of someone right at this very moment, we'd be talking about instantaneous distance. So you say, at this very moment, that person is 15 feet away from me. And it's just a different thing. Okay, it's different than change in distance. It's instantaneous. So what is happening right at the moment? Average. This is unfortunately often what we calculate in school because we don't have really good equipment. We can for distance, but for speed and for acceleration, it's very difficult to get the instantaneous speed and acceleration without, like, say, a speed camera or something more complex. And so often what we do when I say, okay, let's measure how fast you're running, we're measuring the average speed, okay, or the average acceleration. So that's a little different here. Let's look at the averages where the equations get a little more interesting. And actually we're going to represent the average with a line on top. Not a line with an arrow, just a line on top. And at first all these like deltas and these lines on top and these arrows here and the subscript F and I are quite confusing, I would say, and brings a lot of confusion to it, to all the equations. that you can see over here. I have the equations printed out here. But because this could be just v equals d over t, it'd be so simple, instead of v bar equals delta d over delta t. But you'll see that later on when you're actually answering questions, I think that this is quite a bit easier to understand, because there's some things where there are change in velocity, some things that are final and initial velocity. There's going to be average velocity right here. And so I think you're going to find that it's actually better to distinguish them all right now. So delta d, the average, is just the way you calculate any kind of average, like the average on 2 tests, for instance. You'd add the 2 tests together, divide by 2. If you had 3 tests, you'd add all 3 of them together, divide by 3, that sort of thing. So the average distance, if we know the final and the initial, we just add them together, divide by 2. And you'll be happy to know that's the same with speed. The final plus the initial divided by 2. And the same thing with acceleration. The final plus initial divided by 2. Now, I left a little bit of space here because this implies something here, especially with speed here, because we'll be talking about speed a lot. So this is only true. You can only say the average speed is the final speed minus the initial if the change in acceleration, so if delta A, if the change in acceleration is 0, meaning that like for instance, in track and field, when you're running the 100-meter race, you're starting at 0, and then let's say you get to whatever, 13 meters per second. No, it's very fast. Let's say 9 meters per second. Still very fast, but not Usain Bolt fast. So if we go from 0 to 9, that would be true. Your average speed goes 9 plus 0, which is 9, divided by 2, which is 4.5. That would be true if you accelerate at a constant rate, meaning you speed up at a constant rate. However, that doesn't happen in real life, and so we can say this is an approximation of how your average speed, but it wouldn't be true. So just keep that in mind. There are places where the change in acceleration is 0. For instance, when you drop something, the acceleration of gravity is constant. So keep that in mind. And there's another one here. V bar is equal to also the change in distance over the change in time. And so, of course, the delta d we can say is df minus di, and we could say the final is delta t, the change in time is the final time minus the initial time as well. Okay, and we have the exact same kind of equation here. The average acceleration is the change in velocity, not the average velocity, but the change in velocity, which is over here, divided by the change in time. Okay, and we can write that in its full form if you want to. Keep in mind these are another equal sign, so A bar is equal to delta V over delta T, but it's also equal to this. But you can just cover that up if you want to just use this part of the equation. And the last thing here is just talking about constant distance. So constant distance, constant speed, constant acceleration. And this is more of a concept, but this is if d, or if the distance, is constant, the object is pretty boring. It's just stopped. Okay, so not moving. Okay, so if you're a constant 10 meters away from me and I'm stopped, you're stopped too. Now this is in most cases. You could have now if displacement is constant, you could also be going around in a circle and be constantly, say, 10 meters from the starting point. So if the starting point's here and you're just going constantly in a circle, you can always be the same distance from it, or displacement I should say. So this is just normally the case, but you can break that, I guess, a little bit. If v, or if the speed is constant, the object is, you can think of it on cruise control, or you can say, or like a constant speed, right? Yeah, this is constant speed. Or it is stopped. So if v is constant, like if v is 0 meters per second, if your speed is 0 meters per second, then you're stopped. If it's 1 meter per second, then you're on cruise control at 1 meter per second, like you're constantly moving that speed. And the last one, if the acceleration is constant, then the object is speeding up. And that's provided if a is greater than 0. Or it could be slowing down. And that would be if a is less than 0. Or it could be, or it's remaining the same speed. And that is if a is equal to 0. So that's really the cases. If the acceleration is greater than 0, then you're speeding up. If it's less than 0, you're slowing down. If it's equal to 0, you're remaining the same. All right, so this is just kind of introduction to the different things, distance, speed, and acceleration. I wish I was there to teach you about the graphing of these things, and also we do usually we'll do activities that kind of cement this into your brain to experience these kinds of things. Anyway, without that, it's a little more of a struggle, but I'll do my best to teach you how to figure all this out. I'm going to make another video right away here that talks about the general strategy of how to do a method for solving physics problems, but any kind of word problems. And then I'm actually going to start solving probably the first 3 on the page. And then I'll hopefully, after you've watched that and tried them out, hopefully you can complete the rest of them. The questions will get harder and harder as they go on. So good luck.